Hello guys and welcome to another calculus video. In this video we are going to be taking on this very awesome and I consider it sort of a classic integral because you see it in a lot of different places all over YouTube. I'm definitely not the first person who solved this, but it's really fun and it's a really tough problem. The method that I'm using uses infinite summation, and we use almost every single method of infinite summation that I covered in the last part of my infinite summation series. So I would definitely suggest trying this problem for yourself, but if you can't figure it out, don't worry because it is a very tough problem. So without any further ado, let's jump right into it. First, note that the fractional part of x here, with these curly brackets, means x minus floor of x. So for example, for pi, it would be 0.14159, just everything after the decimal point. And the answer to our integral is 1 plus I over 2 times natural log of gamma 1 minus I over gamma 1 plus I, which I know seems weird, but I can guarantee you that this is a real number. So in this video, we're going to be using the fact that the sum from n equals 0 to infinity of some series an is the same as the limit as m goes to infinity of the sum from n equals 0 to m of an, which is something I've used in many previous videos. We also have the fact that inverse cotangent of n equals the sum from k equals 0 to infinity of negative 1 to the n over 1 times 1 over n to the 2n plus 1 all over 2n plus 1, which is the same as pi over 2 minus inverse tangent of n. This is only true for n greater than or equal to 0. And obviously cotangent of 0, that's not really going to work out for this one. So obviously this only converges for values of n less than or equal to 1, or sorry, greater than or equal to 1. So that's what this applies for. And also the derivative of the gamma function, of the natural log of the gamma function, sorry, is the digamma function, which is negative gamma plus the sum from n equals 0 to infinity of 1 over n plus 1 minus 1 over n plus x. So let's go ahead and get started. So the first part is just doing some simple integration. So tangent of x is not very fun to deal with, so we're going to convert this into, we're going to sub u equals tangent of x and convert this into a rational function, as you can see right here. Then, in order to better use the fractional part function, we're going to separate this into the integral from 0 to 1, plus the integral from 1 to 2, plus the integral from 2 to 3 of our integrand, which ends up being the sum from n equals 0 to infinity of the integral from n to n plus 1 of the fractional part of u over u squared plus 1 du. And the reason we did this is because now, in each of these integrals, u is between n and n plus 1, which means that floor of u is n, and the fractional part of u is just u minus n. So we can go ahead and plug that in for the fractional part of u, and we get the sum from n equals 0 to infinity of the integral from n to n plus 1 of u minus n over u squared plus 1 du. And this is super easy to evaluate the integral part at least, and we just get the sum from n equals 0 to infinity of 1/2 natural log of n plus 1 squared plus 1 minus natural log of n squared plus 1 minus n tan inverse of n plus 1 plus n tan inverse of n. Now I'm going to reorganize this a little bit, so I'm going to keep all of this the same, but then I'm going to rewrite this n tan inverse of n plus 1 as n plus 1 tan inverse of n plus 1 plus n tan inverse of n, and then we're adding this extra 1 back. And the reason I'm doing this is because now, if we look at this summation right here, this section right here is telescoping. And this is something I've covered in a previous video. It's telescoping, but if we took the summation of this alone and summed it up from n equals 0 to infinity, right, we would actually get that it diverges, because if you see, the telescoping terms end up being the limit as m goes to infinity of natural log m plus 1 squared plus 1, because that's just the term at the end. So the sum keeps on increasing without bound, but we know exactly the rate at which it increases because it's a telescoping series. This right here is exactly the same story. It's also a telescoping series, and it also increases without bound, but again, we know exactly the rate at which it increases without bound. So we just rewrite this as m plus 1 tan inverse of m plus 1, limit as m goes to infinity. And for this one, we're also summing it up from n equals 0 to m, and then taking the limit as m goes to infinity, but there's just no telescoping series or anything really easy to help us do the summation, so we'll just leave it as a sum right here. So now we have this really weird infinite limit, yeah. And there's a lot of different things in here. So first of all, we see m plus 1 in a lot of places. So since we're going as m goes to infinity, we can replace m plus 1 with just m everywhere, and it won't actually change the value. and it's not too hard to see why that works. Just because, again, we're already at infinity, changing it by 1 shouldn't change the value of the limit if the limit exists, and we're assuming the limit exists, and we'll find that it does exist. So we replace m plus 1 with m, and we end up with this right here. Notice I replaced n plus 1 with n right here, and that just happens after I shifted the index and then added this term at n equals 0. So these two are the same summation, essentially just shifted over by 1. And so now we're going to sort of use our identities here. We're going to replace tan inverse of n with pi over 2 minus cotangent inverse of n. And that's just because cotangent inverse of n is going to be a little bit easier to deal with because we can express it as a power series as long as n is greater than or equal to 1. So then summing up pi over 2 from n equals 0 to m is just pi over 2 times m plus 1. And then the first term of this series is also pi over 2, so we can just write this as pi over 2m, and then this sum from n equals 1 to m of cotangent. So now, ignore all these colors for a moment, but this is our limit at the moment. We have limit as m goes to infinity of 1 over 2, or 1/2 natural log of m squared plus 1, minus m tan inverse of m plus pi over 2m minus sum from n equals 1 to m of cotangent inverse of n. So, this looks really, really nasty, but there is actually a really, really easy way to deal with this. And whenever you have big limits like this, what you should always do is, especially if the limits as something goes to infinity, you should say, okay, do any of these have a nice asymptotic form that they tend towards? So, for example, for natural log m squared plus 1, this is the same as natural log square root m squared plus 1, and as m gets really large, the difference between square root m squared plus 1 and just m is literally goes to 0. So that means that this is going to approximate natural log of m as m grows large, to the point where the limit at infinity is actually equal to the limit at infinity of ln m. Similarly, tan inverse of m gets really, 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 really close to pi over 2, and it gets closer and closer as m grows larger. So this is pretty much similar to pi over 2m. Then this right here obviously is just pi over 2m as well. And this sum from n equals 1 to m, this gets really nasty, but essentially, as n grows large, this approximates 1 over n, right? Actually, cotangent inverse of n always approximates 1 over n. It's just 1 over n plus some other terms afterward, which will all be finite, right? So, if this approximates 1 over n, then the sum from n equals 1 to m approximates h sub n, or the harmonic numbers. And so this is why we wanted to do all this little breakdown of asymptotic forms, because now we can match up different parts of this limit and figure out what's going to cancel with what so that we can get a finite number, even though all of these right here are really infinite. So since this is h sub n and this is ln m, oh, this should say m, sorry about that. This is ln m. We know that the limit of h sub m minus ln m is actually a finite number. That's just the Euler-Mascheroni constant. So we're going to match up this right here and this right here, and we're going to go ahead and evaluate that as one limit, which I'm calling L2. And then, of course, since these are both essentially equal to pi over 2m, we're going to pair up these two right here, and so that's going to be our other limit, L1. So let's evaluate L1. So L1 is the limit as m goes to infinity of pi over 2m minus m tan inverse of m. And then we just reorganize this, so we put pi over 2 minus tan inverse of m over 1 over m. We apply L'Hospital's rule for a 0 over 0 situation, and we get negative 1 over m squared plus 1 minus over negative 1 over m squared, which is just going to be 1 in the limit as n goes to infinity. So L1 is just 1. L2 is where things get a little bit tricky. So again, I said cotangent inverse of n is essentially equal to 1 over n. And we can see this using the power series for cotangent inverse of n for n greater than or equal to 1. So notice I took out the first term here, 1 over n, because it's going to be more helpful to us to treat this as separate from the rest of the summation. So what we're going to have here is 1/2 ln m squared minus 1, or plus 1, minus sum from n equals 1 to m of cotangent inverse of n. So again, we're going to take out this 1 over n term. So now we have 1 over 1/2 ln m squared plus 1 minus sum from n equals 1 to m of 1 over n. Remember that this is just h sub m. So we take these two terms right here, and we separate them from the other terms, and we put them out here. So this is limit as m goes to infinity of 1/2 ln m squared plus 1 minus h sub m. And notice if we take this out right here, we can go ahead and add and subtract ln m, and as I said before, the limit as m goes to infinity of 1/2 ln m squared plus 1 minus ln m is just 0 because these are actually the same. So we can just erase these, and then we just have natural log of m minus h sub m, which is just negative gamma, or the Euler-Mascheroni constant. And now we just have to deal with this other summation here. But one thing you can actually notice is that if we were to actually evaluate the summation right here, we are going from k equals 1 to infinity, so k is going to be greater, so 2k plus 1 is going to be 3 or something greater. So if we were to interchange the order of integration and letting m go to infinity, we'd get something with zeta of 2k plus 1 over 2k plus 1 times negative 1 to the k. And again, zeta approximates 1 as it grows arbitrarily large. So essentially, we'd be summing up negative 1 to the k times 1 over 2k plus 1, which we know converges because that's just a definition of cotangent inverse of n. So I know that's kind of a weird argument here, but another argument here is we know that the overall integral converges, so if this right here converges when we separate it, then this also has to converge when we separate it from the rest of the limit. So we can separate this from the rest of the limit, and then letting m tend to infinity, we get this summation s. And there's a negative sign in front here. So overall, this limit L2 was negative s minus gamma, or the Euler-Mascheroni constant. So if we add together L1 and L2, we get our original integral I was 1 minus gamma minus s. So now we just have to evaluate s. So again, as I just said, to evaluate s, the first thing I always think of when I see double summations is I think, okay, well, let's switch the order of summation and see what it gives us. And that actually doesn't help in this situation because it just gives us annoying zeta functions, which when you have a zeta function, the way you usually solve it is you switch the order of summation. So that doesn't really help us at all. And also, if we were to just evaluate this inner summation, we know we'd just get something with cotangent inverse of n, which may be possible to do. I think there are some tricks with that. But for this, I'm just going to go ahead and stick with what I know, because I don't think that would actually be possible in this situation. So what we're going to do instead is we don't want to have this nasty 2k plus 1 on the bottom, because with this 2k plus 1 on the bottom, that's what gives us cotangent inverse of n when we sum this up. If we sum this up without this 2k plus 1 on the bottom, we just get some rational function, which, as I've discussed in many, I actually have an entire video just on evaluating summations of rational functions, so I'm quite an expert on that. So I would much rather have that instead. So what I'm going to do is I'm going to write this function s of x, and this is actually the summation equivalent of doing Feynman's trick on integrals. So I'm going to define this s of x exactly the same as a summation, except without this 2k plus 1 on the bottom, and instead we have x raised to the 2k. Then, when I integrate s of x from 0 to 1, what's going to happen is we're going to get the integral from 0 to 1 of x to the 2k. It says x to the 2k plus 1. This should say x to the 2k. Sorry about that. Let me fix that, actually. So we have this, the integral from 0 to 1 of x to the 2k is just 1 over 2k plus 1, which is exactly what we had in the original summation. So if we go ahead and integrate our function s of x from 0 to 1, all we're going to get is our original summation back, because we get that 2k plus 1 that we took out, and then at 0, this is just going to be 0, and at 1, this is just going to be 1. So let's go ahead and evaluate this summation and then integrate it. So we're going to start by taking out this lonely 1 over n outside, then reorganizing everything inside of the k summation into something raised to the power of k. So we have negative x squared over n squared raised to the k power. Now notice that this starts at k equals 1, not k equals 0, which means that we need to multiply by negative x squared over n squared, because it's not a true geometric series, because it is missing that first term. So we get the sum from n equals 1 to infinity of negative x squared over n times 1 plus x squared over n squared. Reorganizing everything, we get negative x squared times the sum from n equals 1 to infinity of 1 over n squared plus x squared. And then after doing partial fractions, well, first of all, actually, first thing I did was I shifted the index over by 1, so that we're starting at n equals 0. So we get 1 over n plus 1 plus ix, and n plus 1 minus ix. Then, doing partial fractions, we actually find that we get negative sum from n equals 0 to infinity, 1 over n plus 1 minus 1/2 over n plus 1 plus ix minus 1 half over n plus 1 minus ix. Then what we're going to do is add gamma over 2, add gamma over 2, and subtract gamma. The reason we do this is now if we take half of this term, and then this gamma right here, we actually get negative 1 half digamma of 1 plus ix. And again, if we take half of this term, and then this gamma over 2, we get negative 1 half digamma of 1 minus ix. So we just sort of reorganized everything back into a sum of digamma functions. And then we also have this leftover gamma right here. So we end up having negative gamma minus 1 half digamma 1 plus ix minus 1 half digamma 1 minus ix. So now we just need to integrate it from 0 to 1. And reminder that the integral of the digamma function is just natural log of the gamma function. So this integration is pretty routine. Don't forget the chain rule from this I right here. And when we evaluate at 1 and at 0, we get that our summation s is negative gamma minus I over 2 natural log of gamma 1 minus I over gamma 1 plus I. And we get that our overall integral I is 1 plus I over 2 natural log of gamma 1 minus I over gamma 1 plus I. So I hope you guys enjoyed the video. One thing I do want to note actually is that you can reorganize this using identities of the gamma function into something a little bit nicer, but personally I like this as it is because you can never get rid of all those gamma functions, and so introducing a lot of other functions doesn't necessarily make things better. So I hope you guys enjoyed the video and this awesome integral, summation, limit. We had everything right in this video. And that's really why I love this problem so much, because I get to use almost every single summation trick that I know. And yeah, so I hope you guys enjoyed the video and the problem. If you have any suggestions, please leave them down in the comments. I hope you enjoyed, and I'll see you next time. Bye!